So, good morning. I'm Petr Lukáš from the Technical University of Ostrava in Czech Republic, and I'd like to introduce you the article Demythization of Structural XML Query Processing, Comparison of Holistic and Binary Approaches. This paper has been accepted for publication in the TKD journal. First of all, we work with structural queries, which means that we focus on the tree structure of an XML document and we don't work with character data. The structural queries like X queries or XPath queries are often modeled by twig pattern queries. And there has been an enormous research effort in the processing of TPQs in the last 2 decades. We can identify two families of TPQ processing algorithms. Those are binary joins and holistic joins. The binary joins decompose a TPQ into a tree of operators, the binary joins, while the holistic joins process a TPQ as a whole. So a holistic join is one complex algorithm to process the whole TPQ. We have a simple example here. In figure A, there is an X query. In figure B, there is its corresponding TPQ. And in figure C, there is a sample decomposition of the TPQ into a tree of binary joins. Well, let me talk about the TPQ in figure B. We can see that there is a small tree where the tree nodes are called query nodes, and they correspond to the location steps of the path expressions in the X query. We can see that some of the edges are single-lined, some of them are double-lined, which corresponds to the parent-child or ancestor-descendant relationships. We can also see that some of the nodes are circled. We call them output query nodes, and they indicate which nodes in the XML tree are enumerated to the end user. The remaining nodes in the TPQ are called non-output query nodes. Well, after the 2 decades of the research in the field of TPQ processing, can we decide whether to use binary joins or holistic joins? The binary joins are often criticized for large intermediate results after individual operations. At the same time, the holistic joins are considered as a state-of-the-art because they guarantee an optimal query processing, which is based on some conditions on the time and space complexity. I'll talk about the complexity later. So it seems that the holistic joins are always the right choice, but in our paper we try to show that this is not correct. We try to dispel the most common myths about binary joins, claiming that the binary joins produce large intermediate results after individual operations, and the time and space complexity can be proved only for holistic joins. We propose our binary join approach, which is based on existing works. It is based on an extension of the traditional binary join algorithm stack tree. It is based on the utilization of fully pipelined query plans, and it is based on the utilization of the binary semi-joins. All the techniques are not novel, they have been already proposed, but to the best of our knowledge, they have not been used together to process any TPQ with any specification of output and non-output query nodes, such that the query plan is always fully pipelined, and its performance is comparable with holistic joins. In our paper, we show that for a class of queries, our approach has a linear time complexity with respect to the size of the input, and a linear space complexity with respect to the depth of an XML document. This is the same complexity as for holistic joins, but for a different class of queries. The difference is in the non-output query nodes. It means that the complexity of holistic joins is not influenced by the settings of output and non-output query nodes in a TPQ. Let me talk about the fully pipelined plans. In a fully pipelined plan, the individual operators are implemented as cursors, which means that the result of one operator is consecutively passed to the next operator, and the intermediate results physically do not exist. It turns that the utilization of the fully pipelined plans significantly reduce the memory requirements of our approach. Although there exists work which focuses on the utilizing of fully pipelined plans in the XML query processing, the work ignores the non-output query nodes, which are necessary to be able to consider the binary semi-joins, which I'll describe in the next slide. Let me note that in X queries or XPath queries, usually only a few selected query nodes are enumerated to the end user. For example, in any XPath query, there is always exactly one output query node. So we have 2 types of binary joins, the partial joins and the semi-joins. We can see a difference in this example. In figure A, there are 2 streams of XML nodes, and we can see the pairs of nodes in some structural relationship. In figure B, there is a result of a partial join, and we can see that it's a subset of Cartesian product of the input streams. In figure C, there is a result of a semi-join, which is a subset of only one of the input streams. So it is clear that the result of a semi-join can be much smaller compared to the result of the partial join. One of the basic principles of our approach is to utilize the semi-joins, which is possible due to the TPQ model extended by the output and non-output query nodes. Since the semi-joins are computationally less demanding compared to the partial joins, they, together with the fully pipelined plans, make our approach practically faster than holistic joins in many cases. The basic idea of our approach is to split the original TPQ into a query core and constraining subqueries. The query core is a subtree of the TPQ, which is enclosed between the output query nodes, while the constraining subqueries represent the remaining parts of the TPQ. The query core has to be processed using the partial joins, but with the constraining subqueries, it is possible to utilize only the semi-joins. It means that the less output query nodes add in a TPQ, the more we can utilize the semi-joins and the more efficient our approach is. Well, let me show you some experimental results. We worked with typical collections, which are commonly used in articles on on XML query processing. Those are XMark, Swissprot, DBLP, and TreeBank. You can see the most important characteristics of these collections in the table on this slide. XMark is a synthetic database of auctions, which can be generated with some factor. We worked with the factor 1 and 10. Swissprot is a real database of protein sequences, and DBLP is a database of bibliographic records. TreeBank, this is the most complicated database from the query processing perspective, because it has a highly recursive structure, and it is a database of partially encrypted English sentences. Let me note that for each collection includes more than 2 million XML nodes. For each collection, we generated over 200 TPQs, and we utilized the GTPStack holistic join as a representative of the state-of-the-art. The first experiment is focused on the comparison of our binary join approach to the GTPStack holistic join. We show the experimental results from two perspectives. The first one is related to the ratio of output query nodes in a TPQ. The second one is related to the query selectivity. So let me start with ratio of output query nodes. This ratio, which is depicted on the horizontal axis, means how many query nodes out of all query nodes in a TPQ are output. The query nodes the values represent the relative speedup of our binary join approach compared to GTPStack, and it is computed as the total time of GTPStack divided by the total time of our binary join approach for a set of TPQs in a specific range of the ratio. We can see that if there is a relatively small number of output query nodes, which means that the most of query nodes are non-output, our approach can be, for example, 3 times faster than holistic join. We can see this behavior for the XMark and DBLP collections. All the other collections, the speedup is lower, but on average, our approach is still better than the state-of-the-art holistic join. We can see that with the growing ratio of output query nodes, the efficiency of our approach decreases, but it is still, in most cases, better than the holistic join. From the query selectivity point of view, we can see that our binary join approach performs the best for low selective queries. On the other hand, for high selective queries, it means the queries with a relatively small result, it is usually better to use a holistic join. This is because holistic joins utilize a more aggressive forwarding of the input streams, and thus they can efficiently skip a large number of useless XML nodes. So based on the results of the previous experiment, we propose a simple cost-based approach. According to the query selectivity, we used one of the following 3 techniques. We use the proposed binary join approach, or we use a holistic join GTPStack, or we use a combined approach. The combined approach works such that the query core is processed using the GTPStack holistic join, and the constraining subqueries are processed using the binary join approach. And it is clear that the query selectivity is not known before the query is processed, but it can be estimated. We utilize the sampling estimation techniques to estimate the selectivity of the query. Well, the results of the cost-based approach can be seen in this slide. The figure on the left-hand side has been already shown previously, and it compares the performance of our binary join approach to the GTPStack holistic join. On the right side, we repeated the same experiment, but with a cost-based approach. And we can see that the inefficiency of the binary join approach for high selective query is reduced by the cost-based approach. So it means that the cost-based approach performs almost always better than the holistic join GTPStack. Finally, let me show you one other experiment which is focused on the intermediate result sizes. I said that in fully pipelined plans, the intermediate results practically do not exist. But the individual operators utilize some auxiliary data structures. For example, if you know the stack tree algorithm, you probably know that they utilize some self-list and inherit lists. So they form the dynamic data structures. And in this experiment, we focus on the maximum number of XML nodes stored in those dynamic data structures at one time of a query processing. We call this value as mu-max. We worked with two sets of TPQs. Those are subsets of the TPQs utilized in the previous experiments. Q1 is the subset of queries with only one output query node, and Q_all is the subset of queries where all nodes are output. In this table, we show the worst cases. It means that we show the queries with the highest value of mu-max. We also include the result size and a relative comparison of mu-max to the result size. And we can see that for queries with one output query node, in the worst case, there were 59 XML nodes stored at one time in the dynamic data structures. We can say that compared to more than 2 million XML nodes in each collection, this is a relatively small number, which experimentally proves that the large intermediate results of the binary joins are rather a myth. For queries with all query nodes output, the situation is worse, but this is in compliance with our analysis. We can see that in the worst case, there was approximately 80,000 XML nodes in the dynamic data structures at one time of the query processing, which is much more compared to the Q1 set. But compared to the size of the collections, it is still not an enormous number. So finally, let me summarize the contributions of our work. We proposed a binary join approach using fully pipelined plans for any TPQ with definition of output and non-output query nodes. We proved time, I/O, and space complexities of this approach. We provide thorough experimental comparison with holistic joins, and we show that the proposed approach overcomes the holistic joins in many cases. And based on the experimental results, we propose a simple cost-based approach. And what was the most important, we analytically and experimentally dispel the myths related to the large intermediate results and the suboptimality of the binary joins. So that's all. Thank you for your attention. And if you're interested in more information, you can see the full paper, which will be published in the TKD journal, or you can see the extended abstract, which will be included in the proceedings of the ICD conference. Thank you.